Now that we performed the forward pass through the first two convolutions, our tensor is right here, which we're going to feed it into the C3 module. So the second I run this, M, which right now is still the conv that just came from the previous module, M will become the C3 module, as you can see here. Given that our input is coming from the previous layer only, we'll step over that, as well as profile, since it's false. And now the moment I run this, we'll step into the C3 module, which resides in common.py, right here. So if I run that, now we're here inside the C3 module. Now let's analyze it a little bit. So as you can see here, we have CV1, CV2, and CV3. This corresponds to CV1 right here, CV2, as well as CV3 right here at the bottom. Now we also have M, which is an nm.sequential module. We go here, modules. You can see that it's an ordered dictionary of 3 bottlenecks. So this is a sequential container, and modules would be added in the order that they're passed to the constructor. Or alternatively, you could have an ordered dictionary of the modules. The value of sequential is that it can be treated, the whole container, as a single module. So performing one operation will apply to all the different modules that it stores. And it's important to distinguish it from NN module list, which, as its name indicates, is basically just a list of modules. While sequential have the modules connected in a cascading way. And within sequential, the output of one module will be the input of the next one. So if we jump back here, we can see that we have this ordered dictionary. Now here, the first thing that is going to happen is, you can see here, this is the return of the forward pass. The first operation is going to be CV1. It's going to be a conv class operation. And then the output of that will be fed to this sequential, which has 3 bottlenecks for range n. The number of bottlenecks, in this case 3, comes from here. In the YOLOv5l.yaml, you can see that this is the module that we're in. And you can see the value 3, which corresponds to the number of bottlenecks that will be performed within this module. This can also be seen here in our diagram. And in this case, we're using bottleneck type 1, which are the ones being used for the backbone. As you can see, they're all bottleneck type 1, here as well, and here. And here, and then in the neck of the architecture, you'll see bottleneck type 2. Now let's go ahead and open our Colab notebook to be able to see in much more detail what is happening right here. And we'll do a parallel path as we've done before between our Colab environment and VS Code. So let's run this. And in particular, we're going to go all the way here to the C3 module. Now, the first thing that we're going to do is, in order to start in the same step as we have in our VS Code, we're just going to run our detection model. So click here and run cells in section. And as usual, let's connect to Google Drive. So that will take a moment. You can actually jump into the detection model and see how things are going. So while that is being executed, we can cover what the C3 module actually does in a little more detail. So the 3C module is part of the cross-stage partial architecture, and it stands for cross-stage partial bottleneck with 3 convolutions. That is where the 3 comes from. It is used to enhance the flow of information and gradients across the layers of the network. It also helps in capturing richer feature representations by combining different convolutions and bottlenecks in an efficient manner. So as you can see here, it involves splitting the feature map into 2 parts, and then applying a series of convolutions and bottlenecks to one of the parts, and then merge it with the part that is slightly processed, and then apply an additional convolution to the merge result. Now, the original CSP architecture comes from this paper. And as you can see here on the right, it partitions the feature map into 2 parts that then are merged through this hierarchy. Now, the original paper focused on the DenseNet architecture and DenseNet blocks, which connects all the layers directly with each other, while the C3 module focuses on bottlenecks, as we'll cover in just a moment. So similarly as we've done before, if we want to access the 3C module, given that this is stage 0, 1, and 2, we will call the index 2 out of self.model. Let's do that. Stage 0, 1, and 2. So M2 is our C3 module. Now, in a similar way as we've done before, if we feed in the input image through stage 0, stage 1, and then stage 2, which is C3, then the output of stage 2 will be the output right here at the bottom. So let's run that. And here I'm just outputting the shape of those stages. As you can see, the output of stage 1 and the output of stage 2 have the same dimensions. So the dimension for the tensor coming in will be the same dimension for the tensor coming out of the C3 module. We can also display the architecture of stage 2 C3 module. And then similarly, if we call CV1, we'll be able to access this. And if we want to access M, meaning this sequential module with different bottlenecks, we'll have to call the index first in order to be inside here. So let me show you. So module 2, CV1, this. And then M2.m, and then index 0 will display the bottleneck. So again, we're calling index 0. So this will be our output. And if we want to call this conf, then we can just call that CV1 to obtain that, as you can see here. So again, this is just to show how you can access the different convolutions and the different conf classes within this architecture.